Hey, what's up, guys? This is Cheng here. So today, let's take a look at the LeetCode problem number 156, binary tree upside down. So this is another tree problem, So you're given like a root of a binary tree, and you need to turn the tree upside down and return the new root. So the way you're turning or you can call it rotating the tree is that, for example, you have this one, right? So basically, the new root will be the left child, and then the new root left child will be the current root right child, which is z, right? And then the new root's right child will be the current value. So that's why after the rotation or after the turns, right? After turnings, right? So the new tree will become to y, z, and x. And here we have another examples here, right? And it says that the the steps are done level by level, which means that each level will do the same thing. And also that on each of the node, right, it's guaranteed that we have 0 or 2 child. So the reason being is that if the node only has one child, for example this one, then we cannot rotate this one, or we cannot turn, because to turn a tree, right, upside down, we need 3 nodes. And yeah, so that's why for this one, we have like these examples here, right? So if we turn the tree upside down layer by layer, so the first layer will be the leftmost node, because the leftmost node will be the new root for the new tree, right? Because the left one will always be the new root. So if we traverse it all the way to the bottom, then the leftmost node will be our new root. So that's why the new root will be 4, and then after that we are rebuilding the links of that. So here is just one of the examples, actually. So maybe a more complete example is like this, right? So this is like complete tree. So if we're trying to use this one, similarly, right? After rotating the tree here, basically, so again, this one will be the new root here, right? And then after this one, the new edge will be like this. So and this one is gone. This is gone, and then this is the new root, the new edge, right? This is gone. Okay, and so one more thing is that to be careful here is that so this part, right? So for this part, it didn't change at all, because the rule to rotate the tree is that for the z here, right? So basically, this is the z part. For the z part, we just move it to the left, and we don't recursively do the rotate for this part, because it doesn't make sense. Because again, right? So the tree can only has one root, right? If we do recursively try to rotate this part, so what we'll have like this one. We'll have this one as another root maybe, and this one will have like this one, right? Obviously, this is not a tree, right? That's why we only rebuild the edges for this part, and for the z part we just leave it as it, because we cannot have multiple roots. That's why we just won't do the rotate for the right subtree, only for the left subtree. And that's one thing we need to be careful here, right? So okay, so and since we have decided that we're gonna do the rotate for the left subtree only, so the first thing first is we have to find the new root for the entire tree, which is the leftmost node. Okay, and after finding that, we have to rebuild these relationships layer by layer. Okay, and assuming we have this one, we have 1, 2, 3, 4, 5, right? So let me try to draw this one here. 1, 2, 3, 4, and 5. Okay, so we recursively call the left DFS on the left node. So at the beginning we are here, and then we are coming to here, and then we were at 4 here, right? And whenever there's like no child on the current, no left child on the current node, we simply return the current node, because that will be our new root. So this new root will be 4. So now we return this 4 back to 2. Okay, so the new root is 4 and the current is 2, right? Because the new root will be the root will be returning all the way to the top. So now we have the new root, we have the current, right? So what's left? What's left? We need to rebuild the basically we need to rotate the tree, right? So which means that we have to rebuild the edges from 4 to 2 and 5. And then what is 4? So 4 is current dot left. That's 4. Remember, so 2 is a current, right? And to build the edges, we have a current dot left, right? So what's this one? That's this edge, right? So this edge, what's 5? 5 is current dot right, right? So that's the left. How about the right one? So we have a current dot left dot right. So what is the right? Right, it's just happens to be the current, which is 2. And then after that, right, as you guys can see here, we have some unnecessary edges here, right? Because we have 2 to 5 and we have 2 to 4, which means that we need to remove those 2 edges, right? So we just need to do a current dot left equals to none, and also the current dot right equals to none. So that's basically what we need to do on each of the DFS recursive call here. And so the reason being we use the current left, not the new root, right? It's because if we try to do a new root dot left equals to this one, when we are at 1 here, right? When we're at 1, this is the current. So what's gonna be the DFS return from the previously called? It's also 4, right? Because we remember we keep returning this new root back to the top. If we use the new root to calculate to rebuild the edges here, which is right, because now we're trying to rebuild the edge for 2 to 1, 2 to 3. That's why we need to use current dot left to find the current level that we want to rebuild, right? Yeah, cool. I think that's it, right? So we can start coding, I guess. And this one. So the code is pretty short actually. So DFS, right? So 99% of time when you see a tree problem, it's a DFS. So return DFS root. Okay. So if not current dot left, right? Basically, if there's no child for the current one, we simply return the current, and else the new root. The new root will be the DFS of the current dot left. So these 2 lines here, these few lines here will guarantee that we will always return the sorry, return the new root in the end. So these few lines will guarantee that the the DFS will always return the new root, which is the leftmost node. Okay, and the remaining part is just to rebuild the edges, right? For the trees. So like I said, the current dot left is current dot right. Similarly, current dot left dot right equals to current, right? And then we need to remove the old edge to avoid a cycle in the tree. So that's that. And since we have this kind of special edge cases, and we're not handling the non-current here, because if the root is none, right? So if we do a current dot left, we'll get an arrow exception. That's why we can just handle this special case separately. So if the tree is empty, we simply return none. Yeah. So yeah, I think that's it, right? So if I run the code, accept it, submit. Yep. So I guess for the time and space complexity, it should be pretty straightforward, right? So we have DFS. I think it's going to be a log n time complexity, because we'll be calling these things I think at most log n times. And yeah, depending on the tree, right? So if it's a balanced tree, it's log n time. So, but for the worst case scenario, so what is the worst case? The worst case is like this. We have this one, because each node can only has 0 or 2, right? So I think this is the worst case, right? We have this one, yeah, This is I think this is the worst case scenario. So yeah, I'm not sure the time complexity for this kind of unbalanced tree here. And yeah, maybe I think if the tree is like this one, I guess it's close to n instead of log n, because this one is not a like balanced tree, right? So I'm not quite sure about time complexity to traverse the height for this tree. So maybe log n. Yeah. Cool. Anyway, I think that's everything I want to talk about for this problem. And yeah, I hope you guys like it. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.